So welcome everybody. Good morning. It's my pleasure today to introduce this session about success stories of our project. And the idea is really to show to the community what our project have achieved. So what is the contribution of our funding to this community? So it's extremely important. Change on this one. It's extremely important to really disseminate and show the importance of this investment. It's very important to be able to continue this funding to show that it makes a difference. It makes a difference for the robotics community and for the users as well. So this is why every year we select a number of projects with high potential for the community, for the users, and we invite them to come and present not only the technical achievements that you usually present in scientific conferences, but here it's to present to the audience what result they can reuse as well, they can build on to give them an overview of all the achievement, but also to present the potential use, who are the user of those results. It could be other scientists, but it could also be, hopefully, end users. So what is going to change in terms of product or services thanks to those results? So this is why we invite in this session the consortium representative, but we tell them, if possible, bring with you a user who can also explain how they're going to use the result of this project. So I'm really looking forward to learn more about these results. And initially, when we started these series of presentation workshops a few years back, it was only FP7 project. But this year, this is the first time we also have a first H2020 project. WeMust is the first H2020 project showing results. So here is the order of the Codico was FP7 still, I think. Yeah. So here is the order of the project. Oh. Okay, good. So we will hear more about this project, and they're different each other. So we have Humanoids one, underwaters, the challenges, which is very interesting as well to see a different concept. It's not a pure research project, it's really to also show the concept of challenge-driven research and innovation, to also show how the concept of shared facility can be used if it's a good model to be reproduced, if it shows success, and if it has been selected, it shows success. And then also some in prosthetics. And a project we have invited already some time ago, Safari, because at that time, just at the end of the project, it showed already good potential. There were 2 companies which were launched during the project, so that was extremely successful. And now, a few years after, it's even better because one of the company which was created either during or right after the project, got an award, one of the most prestigious awards from the German president. And so we want also to share with you, it's good to see a few years back after the project, to see how the results have evolved and to different types of activity. And here it's about a company, so that's really good to see this outcome. And finally, ICAP success story. ICAP is a very long story. We started years ago, and it has given many spin-out results. And so we are looking forward to see this all the results which have been generated from ICAP. So I won't take more of your time, and let's go to the first presentation, and this is Codico. So Giorgio, I just realized now that all of them have an Italian component, either the coordinator or very strong.
Thank you. Thanks again to the early birds here that made it to 8:30. I'm here actually representing the coordinator, Francesco Nori, who can't be here also because he recently moved to DeepMind, so has sort of different goals, I guess, at the moment. So Codico is a project that, as I said, was coordinated by IT, and we had a fairly small consortium and actually quite focused. So mainly all partners were somehow involved into control on one side and human or humanoid measurement. In a sense, this project, and you see how it evolved over the years, started with very concrete and focused goal, which was basically develop controllers for complicated humanoids and make in such a way that the humanoid could also measure humans, and so in interacting with them, have an understanding of what the humans were doing. There was another important aspect. Everything was connected to the ability to measure interaction forces, and therefore dynamics was very important in the project. So the tasks that were set at the beginning of the projects are represented in this slide. Very, very simple. There's an evolution of complexity as well. So the first one was simply balancing a robot, potentially again a humanoid, while having multiple contacts with the environment. And in this case, we assume the contacts are rigid, so to keep things simple, in a sense, we simplified the, let's say, the type of contact the robot is having with the environment. The second scenario, let's say the project was 4 years in duration, so the scenarios are roughly one per year. The second scenario was about interacting with the environment while maintaining contacts as for the first year, but having also a goal, which is not just balancing, for instance, but is reaching a goal while the robot is also balancing. So have potentially a hierarchy of goals and satisfying certain primary goals while still trying to satisfy secondary goals. So the robot is highly redundant, so this is possible, or in certain cases might not be possible, but at least the system tries to find an optimum where the primary goal is always satisfied and the others may not be. The third scenario was about non-rigid contacts. Although here it looks like the robot's manipulating something soft, the task was relatively different, is the robot in touch with something that has certain complicated kinematics. Not to the point of human body, but we'll see later, as if balancing on a stable surface, for instance, or on something that can move while the robot is trying to balance. And the fourth and last scenario was interacting with people, whereby this complex kinematics becomes a human body, so potentially very, very complicated. And here, let's say the expertise of the consortium in measuring human body became fruitful because as part of the work there was also an attempt to sensorize the person, so in such a way to inform the robot about the forces or the torques that the person was generating. So this is the first video, which represents the first year result, which shows one relatively simple example. Here the technology that we developed was the following. First of all, estimating external forces, so estimating interaction forces of the robot with the environment. This was possible because we have enough sensors. In particular, on the ICAP, we have 6 force-torque sensors, each 6 degrees of freedom, plus a full-body sensorized skin that can be used for both for measuring the position of the contact forces, and also it can give additional information about the intensity or the amount of force that is being exerted. And this is the first example. I I mentioned dynamics earlier because here, in order to basically take the measurements that can be skin or force source sensors and project into the control space of the robot, the joints, we have to take into account the body dynamics. And so one of the technologies was developed was computation of inverse dynamics very efficiently, which nowadays is kind of possible with standard computers, so nothing particularly dramatic, but was important as a piece of technology to be added to the robot. The second year, as I said, was about achieving a goal while satisfying a primary and more important goal, which in the case of the humanoid is maintaining balance, and in this case the secondary goal was reaching for a visually identified object. And so we see the robot here that is, let's say, moving the entire, in a sense, upper body and trying to reach for an object while it's maintaining balance, and while potentially it can be also disturbed by a person interacting with the robot. So again, and you see some of the examples where the robot is disturbed. Again, measurement of external forces, the important piece of technology that was developed here. For year 3, we decided to complicate things a bit, and what you see here is the robot balancing on a seesaw. Here, must say that the object was kept simple because the project had no learning component. So here the model of the only thing that can be, let's say, estimated automatically by the robot was the axis of rotation of the seesaw, which is very simple, basically one parameter that was used then to build the controllers. But again, interestingly is to take the robot dynamics, the dynamics of the interacting object, let's say, and combine them in such a way that the robot can eventually maintain balance. And even when disturbed a bit by the nasty experimenter as usual. Last but not least, on the 4th year, we started developing technology to measure external forces generated by humans, but also by measuring the state of the person. This is a sensorized suit, and in this case, we had also force platform that was utilized, and what you see in the displays is basically estimated torques by having a model of the human body and projecting whatever measurements we had, the forces, external forces, into the joints of the person. This information here was simply used to basically improve the knowledge of the contacts by the robot, but we see in a moment that we were able also to basically build more complicated tasks. So basically at that point, the project was finishing, and Francesco and the group working on Codico had ideas on how to extend this into a proper human-robot collaboration. So here the idea is that since they started developing this sensorized suit that can give information about forces generated by the person, potentially on object or directly on the robot, there's a possibility of doing human dynamics estimation, and this information can be sent to the robot, and the robot can generate appropriate forces as well, taking into account the state of the body of the person. This is shown here where we have a task where again, the robot has to get up and is being helped by a person. And of course, depending on how much force is being applied by the person, the robot can take this information into account and generate more or less force in order to get up appropriately. So this led basically, this was a result of Codico and led eventually to a new project called Andy. This started last year, and why is interesting? Because while the first project at Codico was very, very focused on research, basically, all partners were research partners. This one started to approach, in a sense, more industrial application, and in fact, half of the consortium is made by industrial partners, by companies. Xsense is the company that is providing the sensorized suit, basically. And then there's Autobock, they're developing exoskeleton, and there are IMK, there's a company doing ergonomics, and again, interested in measuring the human body for ergonomics reasons. And Anybody is another company that is developing simulations, very sophisticated simulation of the human body. INAIL, I don't know, for the Italians is obvious, for the others is the major national workers in insurance in Italy, very large. And again, for this specific projects, they're doing exoskeletons and ergonomics. So, I mean, there's a concrete application in going towards, in particular in this case, 3 scenarios in Andy. One is clearly, let's say, the more research one, measuring the human body and measuring the interaction with the robots. Another one is exoskeletons. Again, there's interaction between the machine and the person. And last but not least, there's one of the scenarios which is on cobots, collaborative robots. So in a sense, there's a trend. The project started, as I said, very, very focused on the research aspects, on control theory, basically, and is evolving towards application of these controllers to more concrete scenarios or real-world scenarios. As I said, the project started last year. The first review, don't remember, I think there's a review in April for Andy already, and so work in progress. Thank you.
The next one then is Walkman. While we are changing speakers, we have time for 1 or 2 questions to Giorgio. Is there any question about the project, about the results, how to use the results, the application? Any question? Yes, there is a question, Paolo.
It's both. We're doing sensory fusion. There are both the Force-Torque sensors being used and the skin, and also gyros and accelerometers when we have it. So actually the project developed the framework for doing sensory fusion utilizing whatever is available. So depending also on the configuration of the robot, you can plug in more or less sensors and obtain better or worse results in that case.
I have a little question about safety. So what is the perception of the Association of Workers or whatever from Italy? So how do they perceive that? Do they feel that there is some safety issue, or what is their...
Well, in that particular case, they're interested basically only in more the ergonomics part and the ability to utilize exoskeletons. So it's not... I mean, the interaction is more on the wearable and also how people exert forces while doing certain tasks. For them, of course, safety is very important, because if they can reduce, since they're insurance, if they can reduce the number of injuries, of course, for them there's a saving. But they're also doing like prosthetics. They have a range of, they're working on rehabilitation. So there's a range of potential application. For Andy specifically, they focus on basically on one task.
Right. So they're not in the cobot scenario?
No, they're not on the cobot scenario, yeah.
Would be interesting to see their views on the cobot, but at a given point, yeah. Thank you so much. Thank you again. So now the second presentation is about Walkman. So Nikos, the floor is yours.
Thank you very much. Good morning to everybody. I'm happy also to be here to give you an overview of the Walkman project. I'm Nikos Agarakis from IT. I was the coordinator of Walkman, and I will give this presentation on behalf of the World Consortium. So I will try to give you basically an overview of the project and what we did actually and what results actually, as Cecile said in the introduction, can be reusable in future projects. So starting from the figures of the project was actually a small IP. It was only 5 partners that started back in 2013. It was 4 years duration and actually attempting to address some of the objectives of the ICT 2013-10 call related to the motion capabilities, manipulation, locomotion, but also looking actually a lot on the physical robustness of the system, how we can make it capable to executing real tasks, and eventually link these actions to perception. So the idea was actually to demonstrate these new advancements actually inside the platform that it has a humanoid form, and demonstrate what I said before, this capability to execute real tasks like the requiring strength and power similar to those that can be demonstrated by an average adult person. At the same time, of course, one of the key technologies we'd like to explore was actually to have this whole body locomanipulation concept where all the bodies is interacting with the environment, but at the same time generate motions to execute both locomotion and manipulation, and link these actions, as I say, with perception and try to explore this system not only inside the lab, but also go to more realistic, let's say, environments. So we start actually with leveraging on basically two main let's say, key technologies. I mentioned already hardware performance. It was actually, to us, it was very important to have a system that is not fragile, is not slow, and it can actually execute real physical interactions that sometimes can be very harsh, reaching the impact, let's say, situations. At the same time, we want to achieve this actually strength and physical performance within a body that is actually very close to the body of the human, and this robot can actually go through doors and navigate inside the human environment. The second actually key technology was locomanipulation control that actually involves 3 main aspects. The first one is actually the generation of these whole body motions to benefit both the locomotion and the manipulation of the system, but link this to locomanipulation affordances, how you can explore the possibilities of interaction with the environment to assist this locomotion and manipulation, and combine these motions actually forming a motion description language that allows you to formulate complex behaviors. This slide shows an overview of what of the, let's say, 4 most significant results. I will give you more details later. Of course, starting from the hardware performance, which actually resulted in a state-of-the-art humanoid system, going to whole body locomanipulation, particularly the taxonomy of support poses, how the robot can actually explore the environment to balance and locomote and pass over the obstacles. The affordance-based interface, that's the next level of, let's say, pilot interface that allows you to mix semi-autonomous operation with the pilot commands in order to faster the execution, and of course the locomanipulation-based principles that we develop based on neuromechanical primitives, mixing periodic gate generations with reflexes during the locomotion. So this actually was extensively published in many, let's say, highly ranked papers, and we had several keynotes on all of these 4 different topics and conference, with a total of 183 scientific publications, where, I mean, you can see that some of the statistics there, 50 of them about journal papers, and the rest, actually, most of them was actually in highly ranked conferences like ICRA, IROS, Humanoids, and RSS. Okay, I mentioned already the publications. Of course, this is actually recognized with a number of best and finalist papers. The last one actually arrived yesterday, is a European selection of young innovators that is one of the PhD students that work in the project. So it will happen later this year, but actually I just received the email yesterday. We're very active actually to disseminate in workshops. So actually, Walkman, I mean, we produce a very big number of let's say, organizations in terms of workshops at conferences. Basically, we're present at any conference, major conference from 2014 and after, and more than 20 of them was actually, as a first organizer, was coming from the Walkman Consortium, showing also very nice interaction with the other European projects that work in similar areas. Dissemination, actually, of course, apart from the scientific part, we also show this to the public and actually massively, let's say, disseminating also in major networks, let's say, the experimentation of the robot and the results during the years. Another actually big effort to put is actually really to show this to different places, the results. So we went many times outside actually to show to the public, but also of course inside IT during several visits and exhibits, both for the purpose of the experimentation, for example, the experiments in the site of civil protection bodies, but also for the purpose of other demonstrations to the public. Okay, now going back now to the results, actually I started for the robot that you can see actually the final form here. I have to mention here that basically the most important achievement is actually that we have now a humanoid that basically can really execute a real task. And you can see some of the specifications of the power strength capacity. The arm payload is actually really exceeding the 1 ratio to the weight of the arm. The robot is also actually equally very fast, so that can really execute really aggressive, let's say, motions in interaction with the environment. I mean, just to mention the total power that we have on board, of course, this is a peak power in the total actuation units, and is actually really resilient against impact. So you can really execute really tough tasks with the environment without breaking the robot.
We developed methods for the generation of whole-body multi-contact motions for humanoid robots. Here we propose a taxonomy of whole-body human support poses, which together with human motion capture data with statistical models used in natural language processing allow the very efficient generation of sequences of multi-contact poses in the context of local.
So basically here, as you can see here, is the idea was to create, let's say, a taxonomy of support poses and how to use this actually to support the robot while passing. Of course, this is an obstacle that is actually not really significant for the average human, but actually demonstrate the principle of this entire use of robot to interact with the environment to support locomotion balancing that can be, let's say, critical in cases that you need to enter really unstructured environments.
To develop these control algorithms, we follow two different approaches. In a model-based control approach, we put all the mechanics of the robot into a single mechanical model, and then we use this mechanical model as a base to drive walking gates and control algorithms, all in a very modular control architecture.
In another approach, we use the inherent symmetries that all humanoid robots share to develop a family of walking gates. Both algorithms, which have been tested on the Coleman robot here at EPFL, are easily portable to the Walkman robot.
Eventually, these control algorithms enable the robot to navigate through the environment and perform the search and rescue missions that are assigned.
So the main actually contribution here is actually, as I mentioned, the mix of this, let's say, periodic with reflexive motions based on neuromechanical models to generate something that is, let's say, more reactive or more adaptable, let's say, to different disturbances.
The Walkman project is concerned with the development of methods for increasing the level of autonomy of humanoid robots operating in unknown environments. For this purpose, we developed a perception and affordance extraction pipeline, which generates a set of interaction possibilities of the robot with the current scene. We call these interaction possibilities whole body affordances. These whole body affordances can either be used by the robot to autonomously select the next action or pass to a human operator controlling the robot via a pilot interface, as we demonstrated that on the Walkman robot. So in the second...
another actually important, let's say, contribution to the project is actually the validation effort that we put on really demonstrating the system and actually outside the lab. And of course, probably many of you know that we start actually very early in the project with the DARPA Robotics Challenge that we went there with Walkman build really less than 1 year and design and build to participate to the challenge. Then we have this whole body locomanipulation challenge that I showed you before in previous slides. But the real test was actually happening in Amatrice, where actually you have a field test of the robot inside, let's say, a damaged building. And this was actually really a scenario that you can consider for, let's say, for application for the robot and originally actually planned for these purposes. This is actually the building that we try to enter and inspect. and it's based in Amatrice village that was actually hit by the earthquake about 2 years ago, and was basically quite, let's say, unstable. Like you can see, the walls are really damaged, the structure, and so on. The task was executed in collaboration with the civil protection bodies in Italy that was actually not a partner in the project, but was actually, let's say, a consultant and end user for us since the very beginning in the activities of the project. The actual scenario involved the phase 2 of disaster response. Of course, we are too slow to enter, let's say, and save lives at this moment, but actually there are critical, let's say, activities that are happening, let's say, in a secondary phase of disaster response that takes 2 and 3 months, and this is related to the inspection of the buildings. So actually going inside the buildings, checking the stability, retrieving, let's say, objects for the owners, and this is actually really very risky for the emergency responses, because many times these buildings are unstable. There are secondary earthquakes that are happening quite often after the main one, and actually in one of the first buildings that we attempt to inspect was actually the Bank of Amatrice. We went there to check the area inside the building, and 5 hours after we left basically the village, there was a secondary earthquake and the building collapsed. So then we have to change and move to another, let's say, house that was actually in a close vicinity of Amatrice. So yeah, this is actually some, let's say, data about the place. What we have to do, we got to go inside to do these crack measurements, check, let's say, the orientation of the different planes in order to understand, let's say, if the walls and ceiling, with respect to the ceiling, has changed, let's say, the actual orientation, and to recover some object for the people. This actually shows the setup, actually, the teleoperated station outside.
Task.
The video doesn't play.
System
Antonio was
has been
describing
used in real life operations, both in the DARPA Robotics Challenge in 2015 and in an even more realistic environment in Amatrice after the earthquake, to explore a house that was partially damaged, destroyed by the earthquake. The robot could get inside, and through our controllers, with a pilot, a human pilot that was safely outside the house, could see the scene and assess the stability of the building, also retrieve some of the objects that were left abandoned there.
Okay, I will go fast because probably the time is not much. So this actually shows, let's say, some snapshots of the 4 tasks that we have in the final scenario. Of course, this was mostly built inside, let's say, it was not a fully realistic environment, but it actually involves manipulation tasks that has high payload. For example, the opening of the door required like 6 kilograms force for the robot to push, or the bridge was like 2.5 kilos each, and those other bimanual tasks actually that related to the extinguisher or the bridge removal and so on. So this was actually done towards the end of the project at the end of last year. Okay, a few words now about the technology transfer actually that we also did inside the project. One of the key components is actually the actuation system that you can see here, what is actually capable of doing, showing already a technology, a reusable result that actually this upper board that you see here is actually the one that it was developed to install on the Cendavro robot that is done in another European project, showing the high power density, 10 kilograms payload, of the arm that weighs like 9.5 kilos, interaction adaptation at the same time is very harsh to interact with the environment, break actually, that you may need to do during this disaster response operation, where you need to sometimes to modify the environment in order to release the situation. We developed a full family for this, with giving these fruit names actually, so showing the capabilities of the drives are really at high technology readiness level that I can say close to 7 to 8, and the actuators now actually are also available through IT Technology Transfer Office. The same applies for the sensor components that we developed for the project, 6-axis or 6-axis joints that we're actually really providing this to customers, although there is no still yet a company, but it is done through the Technology Transfer Office of IT. We had the booth at ICRA that actually demonstrated this to the research community, both the actuators and the sensors that they are used in the robot. And following this, we have several requests, so we're already providing these sensors, but also the actuators. And we formed this actually website at Robotics EU, that where you find all the detailed specifications of the drives for the actuators and the sensors components of the robot. Another result that actually can be high potential to be reused for other projects is actually this next level of pilot interface that makes this semi-autonomous based on potential, let's say, interaction with the environment, the affordances, with the commands from the pilot. And this is actually work done from KIT, and it's actually already exploited in other European projects and national projects. XBot Core is actually also a software architecture for real-time control of robots that we develop. Provides built-in interface for several middlewares like ROS, YARP, and Orocos, and it's actually easy integrated with simulator tools that makes really seamless transfer from simulation to the real robot. It's an open source, and actually you can get more information to this site, and also conduct is there for all those that are be interesting to use it. Our whole body control framework, actually, which is also a library that is actually open source available to generate whole body motions, that actually is not only restricted to the motion generation, but also generating also impedance profiles for different parts of the different effectors of the robot, but also the null space of the robot mixed in one library. Again, is available as open source, and you can actually find demonstrations and also documentation for the library for potential use, and it's already exploited in other European projects. Okay, so to close summary, all the components of the robot that are used in the robot, they are already actually explored in several projects. Sendavor and Cogimon will use the same basic technology. Walkman will stay active in Eurobench. It's actually a new project that started actually recently that will be, IT is involved, and we have to provide this benchmarking facility for leg robots, and the Walkman will be one of the standard platforms to exploit these benchmarking capabilities. Simulation tools also will be exploring in all three projects. Open source is already exploring Cogimon and Sendavor, and the same is for XBot Core, the real-time architecture. Locomotion principles developed by EPFL already exploring inside Cogimon, and also I mentioned already the affordance-based interfaces on several national and European projects already used. This is actually to say thanks to, of course, to the entire team that was actually really composed by highly motivated people. Of course, to the project officer and the reviewers for a very fruitful collaboration that we have all the years, and to the civil protection bodies that support us from the very beginning of the project. Thank you very much also to you for the attention.
While we move to the next session, the next presentation about an underwater robotic system, which is completely different, is there any short question to the presentation, the former presentation, to Nikos? Oh, yes. Rich.
Yeah, you said when the slide about the affordances, you said there's a national project looking at using it in collaboration with nuclear decommissioning. Yes.
Thank you. While we're transitioning, I just wanted to inform you actually that the session are recorded and they will be published afterwards. So it's very nice to, as a remaining something remaining from this presentation. Good, so the floor is yours, Giovanni.
So, if I can stand here, sorry. So thanks for the invitation to this session and for the introduction. The project name, as you see, is Widely Scalable Mobile Underwater Sonar Technology. And it's an H2020 project. I have, given the time that is kind of short, I have an introductory video that I will show you immediately to give you a sense of what the project is about. And then I will transition to the discussion on exploitation.
The seabed is the last unexplored frontier on our planet. High costs of research in the marine environment, the use of bulky equipment, and lengthy stretches of time at sea are some of the main obstacles that have so far hampered the systematic study of the sea depths. To overcome some of the problems encountered in seabed mapping, sea floor characterization, and underwater seismic exploration, the 3-year Why Must project was launched in February 2015. WIMUST stands for Widely Scalable Mobile Underwater Sonar Technology, and it aims at developing a system based on a heterogeneous team of cooperative, autonomous marine robots for geotechnical surveying and geophysical exploration at sea. The project plans to use two different types of vehicles optimized for the occasion, the Folaga and the Medusa. Traditionally, seismic acoustic surveys are done using a vessel that tows a powerful acoustic source and a group of streamers equipped with hydrophones. The acoustic source generates a sound that penetrates the sea bottom, and the consequent echo is picked up by the hydrophones mounted on the streamers. This setup results in a sort of acoustic antenna, having a fixed geometry depending on how the streamers are towed by the vessel. The idea behind the WIMUST project is to decouple the source and the streamers, mounting the latter on autonomous underwater vehicles, AUVs. In this way, the streamers can be carried closer to the sea bottom, improving the acquired signal's quality while using acoustic sources of lower power, and therefore of possibly lower impact on marine mammals.
Yeah, so I think this was hopefully sufficiently clear to describe the application. The images you saw from the ship are taken actually from one of our partners, CGG, that is pushing to exploit the results of this project. These are a couple of details. The project actually started in 2015, 1st of February, so it ended 31st of January this year, and we are in the process of wrapping everything up for the final review. The consortium is made of 9 partners, 4 are academic and 5 are industrial. This is how they are distributed in Europe, and these are the long names that I will not read because of time. Just let me mention that the academic partners are mostly universities from computer science, marine robotics, and signal processing, acoustic signal processing. This is Syntal. And the companies come from either geophysical exploration, CGG, GS, or geomarine, or from the robotics industry, so Graaltech and Evologics. These are the name of the principal investigators only. Of course, the number of people working on the project is much larger than that. These are a couple of pictures from our early meetings, and by the way, in this one, you can see this is the first time we actually deployed our AUVs with the streamers. So the streamers are these cabled, they are oil-filled to be neutrally buoyant, and they host the hydrophones that pick up the sound from the source. Other pictures of other experiments you see with the same robots, and this is the last one, which is the worst in terms of image quality, but it's my preferred one because it was taken in occasion of the last experiments. So we were tired but happy, so to say, in this occasion. We have a project advisory board that helped us a lot, especially in the early stages of the project. Frank Ehlers, Luis Wittcomb, and Jens Hoven. They cover basically both the robotics part and the acoustics part. Regarding the partnership, ISME is my own institution, is coordinating. It's a network of universities rather than a single entity, and the same holds for Syntal, that also has a linked third party, but this is a technicality. The big picture, well, I showed you already what the situation is traditionally for this kind of acquisition. Maybe I should mention that what you saw in the initial video was the large-scale system. So this kind of technology is used basically on 2 scales. The large one that you saw with the large ship carrying these long streamers, when I mean long, I mean up to 10 kilometers long. So that system you saw with a ship is one of the, I've been told by our CGG partners that that is the largest man-made item that is moving on the planet to date. There's nothing larger that moves on our planet. So the streamer can be, let's say, the array can be 1 kilometer wide and up to 10 kilometers long. So you can imagine the complexity also of maneuvering the ship for this kind of system. That scale is used for oil and gas exploration at very large depths. So they can, the water column can be up to 4 kilometers depth, and they are able to penetrate the seafloor 4 kilometers, a couple or 2 or 3 kilometers. So the source power is also very, very high. You can now scale the whole thing of 2 orders of magnitude, and you get what is used for so-called geotechnical surveying. That is what we are addressing. So the streamers are long 100 meters. In our case, they were actually shorter. They were 20 meters because the AUVs are small. And the water column is in the order maximum of hundreds of meters. And the resolution is much higher, so they use higher frequency sources, and this is used to characterize the terrain for civil applications mostly. So now there's a big business, especially in the northern seas, to characterize the seafloor for installing wind farms at sea, for instance. So there is a large interest, industrial interest for this kind of application. Now the challenges in decoupling the source from the streamer, in the traditional technology, as you saw, they are attached to the same network. If you decouple the sources from the streamers, from the one hand, you have much more flexibility because you can change the shape of this antenna, and that's exactly what the signal processing people were eager to do in this project, and we did. But on the other hand, you don't have a physical link to be used for synchronizing the sources and the receivers, because the processing that is done is based on time of flight, basically. So you need to accurately know the timing between the source that emits the sound and the receivers that are receiving it. So one of our major technical problems was on clock synchronization. Avologics in particular, this German company working on acoustic communications, worked this out in depth during the first half of the project. We tried to solve this with the traditional network synchronization methods, but we ended up noticing that the resolution we needed was not reached. So let's say the brute force solution was installing atomic clocks on all of our modems. This, was an issue, both technical and, let's say, also on the finance of the project. We need to reschedule some of our expenses. But as an outcome, now that given that we're talking about exploitation of the results, Avologic is now, let's say, able to claim that they have this item, and the TRL level is 9, according to what they told me just a few days ago. So they are very happy about the fact that they had a chance to work on this in this project. From the robotics point of view, the main challenges were on cooperative control, because these streamers need to be, of course, synchronized and cooperate with a source. And the problem in doing this cooperation is that the bandwidth, acoustic bandwidth, is very limited. So we don't have Wi-Fi, of course, underwater, and the acoustic modems can only give you a very, very limited throughput. And by the way, they cannot, let's say, transmit all concurrently because they would interfere with each other. So we had to design an architecture, scalable architecture, and to make the long story short, we needed to have 2 modems working on 2 different frequencies. The low frequency one or medium frequency one is used by the vehicles only in listening, and the ship or the surface vessels are transmitting on that frequency information that is used for navigation. And given that the vehicles, the underwater ones, are only listening, we can scale to a larger number of vehicles. We used 7 in our project, but the architecture is ready to be scaled to much larger numbers. Okay, I will not go into the detail of this. As I told you, the big bulk of work was on integration. I have a large number of slides on integration that I will skip, and I will just show you the final video on the experiments. All this is on integration. Just to mention, we had items coming from different companies with different robots and needed to be integrated in one system. So this was a huge work in terms of hardware and software. It took us basically the whole third year of the project. And this is the design of one of our experiment, or of the final experiment. This picture is basically showing you how we performed this experiment. So in the end, we had 2 autonomous catamarans that are the ones you see up here carrying the sources. And then we had 4 underwater vehicles with the streamers and 1 surface vehicle that was aiding the underwater navigation with GPS. So this is what in our language we call an anchor node. Just a short video, and I will close it here, if I may take a minute. Yeah, there is nothing spoken here, so I can turn this off, and I can describe. So this is when we deployed the vehicles. We went out at sea, about 1 hour navigation out of the port. This is Sines, south of Lisbon. And we performed a survey, geotechnical survey, so of the smaller size kind I told you, scanning an area that was about 100 by 200 meters, which is typical size of what is done industrially. And we did this with 4 submerged vehicles, 2 Medusa, 2 Folagas, 2 autonomous catamarans. Each one was carrying a source, so we have 2 sources, which is helpful not only for the acquired signals in terms of seismics, but also for the navigation, because we can actually localize the vehicles having these 2 sources. Yeah, this is what, oh, sorry, it's not going there, it froze. Okay, I had another slide, but final one, but I guess there is something wrong with the projector showing the results. It's showing something different from what I have here. I don't know why. Yeah, it's interesting. Maybe we can do it the hard way. Yeah, let's try. Many years of computer science and then... Okay, sorry, but I mean, I just had one final slide showing an example of the acquired results. It's this one, and I would close it here. I used already more time than I was supposed to. But anyway, our partners, especially the CGG, is this large company. They are in oil and gas surveying. They are very eager to exploit our kind of technology. And they were not worried about the quality of data we would have acquired. They were pretty sure that this was feasible. But they were, and this is interesting, I think, for us, for the robotics people, they were actually more worried about the performance of the robots. They were asking themselves, will the robots be sufficiently accurate in their navigation and reliable to actually replace the traditional system? And I believe we demonstrated that the answer was yes. So we are all satisfied about that. Okay.
While we move to the next one, Yurok, about this challenge project. Is there any question? Quick one? Because we're a bit short of time. Oops. No problem, no problem. It's super interesting.
Okay. Thanks very much, Cecile, and good morning to everybody. So this is the EUROC project. It's European Robotics Challenges, which I remember that I gave a presentation in Vienna, if I remember, at the European Robotics Forum. So it's nice to be back because the project is about to end in June. So it's like, it was originally 4 years. It's been extended to 54 months and for a total budget of 16.5 million. Should I use this one? Yes, okay. So what is EUROC about? The motivation for the project started from observing that the European manufacturing industry, actually we are pretty strong in terms of using robotics technology in industry. And this is also because of many success stories of technology transfer from research labs to industry, and both SMEs, mid-caps, and big industry. You will hear later about results of the Safari project in which also our team was involved. So the idea of EUROC was to favor and to announce and to boost this technology transfer using something which the Americans and in their culture have really nurtured in the years. So it's the using challenges as drivers for innovation. Of course, you heard about Walkman taking part to the DARPA challenge. So the idea was to create a kind of favorable environment here in Europe and just to get all the stakeholders in the value chain to work together within this project. So we launched 3 industry relevant challenges back in April of 2014 through a mechanism of the open calls. For those of you who have been in the game for years, you remember that we had a project back in 2009 to 2013. This is the ECHOD project, which was a pioneer in terms of the cascaded funding. One of the open calls now is about digital hubs, and this is the funding supporting third parties, financial support to the third parties, and ECHOD was a sort of pioneer. So we adopt the same mechanism of the open calls and try to get more stakeholders to the project. Each challenge has been thought in 3 increasing stages in terms of complexity, and symbolically, only symbolically, the project will end with 1 winner. Let's take a look at the challenges. The first one is about reconfigurable interactive manufacturing cell. If I want to use the robotics lingo, this is human-robot cooperation, human-robot interaction. The second one is about shop floor logistics and manipulation. From a technical viewpoint, is mobile manipulation. The third one is about plant inspection and servicing. From the robotics viewpoint, is using aerial technology, so drones, quadcopters, and so forth. And each challenge involves the whole manufacturing supply chains within their own field. And again, the technology transfer is kind of boosted. So we organize 3 increasing stages in terms of complexity. The first one was just to get to play on a kind of normal, uniform field. We carried out some benchmarking exercise, and this was in terms of a simulation contest. So we had the qualifications from the challenges. In the second stage, we were using some common platform. So we had all the teams different from the previous ECHO project, for instance, in which there were 51 independent singleton experiments. The idea was to have all the teams, all the challenges playing on the same, in the same game, on the same cluster, on the same platform. So this is stage 2, which we call realistic labs. And then some teams were promoted to the final stage, and the experiments were taken to the field test for the real test, and also the idea is to ensure sustainability and adaptability. You will hear later about one of these step changes in the project by Federico Vicentini from ETIA CNR. Who is part of EUROC? We had a core consortium in which we put together research organizations, technology providers, system integrators, and altogether we provided management and organization of challenges, hosting the platforms and providing the tools, and more importantly, supporting the challengers engaged into the 3 challenges. So we had research teams, we had end users, we had technology developers, and also specifically for challenge number 1, whose scenario was quite open in terms of human-robot cooperation, we also had system integrators come to the project. So on top of the core consortiums, we had the challenger teams. Let's take a look at the core consortium. We have partners from Germany, KUKA, Hashtag, who is part of Intel now, DLR, and IPA Fraunhofer. We have one British partner, Innocentive, and they are very much engaged into challenges in the US, and they have their EMEA subsidiary in UK. We two Swiss partners, ETH Zurich, and a former Alstom inspection robotic, which is part of GE. We have LAS CNRS in Toulouse, in France, and we have an alliance of 5 universities, 5 southern universities under CREATE Consortium in Italy. So this is just to give you an idea of the challenges that were involved. You will recognize many logos you have seen in the previous presentation, you will see in the next presentations. So in a way, we were able to take just both big companies, small and medium enterprises. I forgot to mention that Europe is also part of a European initiative, which is called I4MS, ICT for Manufacturing SMEs. And in fact, some SMEs were involved, but also like a big research organization like CERN, for instance, in Geneva, has been involved in one of the experiments. So let's take a look at the challenge chart. Those are the 3 stages which I mentioned. So we had a simulation contest. We had some kind of seed money to reimburse the work done during the simulation. And also we had one topical event, which was described yesterday in a specific workshop on challenges and competition by Fabrizio Caccavale, our scientific coordinator. And this was a brokerage event which took place in London, in which we really brought together all the qualified challengers from the simulation contest and the end users and the system integrators and the technology providers. And this was a matchmaking event which really worked out quite nicely. And the good news is that the teams were formed to work on the proposal, and also this was like an opportunity to really get new people to work together, which is one of the ultimate and most noble goals of European-funded research, especially as opposed to research in the US. And to some extent, Asia is a sort of different, is a world apart. So in the second stage, we had the challenge teams, and they got support, 15 qualified. And the third stage, where we are now, it's in the final stage, in which there are only 6 challenge teams. But I can tell you that some of the teams that work in the second stage are continuing to work without our financial support, and this is quite nice. So what are in one slide, the project lures? Of the 16.5 million, 7 million went as available to grant money to the challengers, almost complying the current rule of the digital hubs, in which 50% of the budget must go to third parties. So in a way, we were implementing this kind of system. So compared to the American challenges, in which there's like one winner and one big cash pot for prize, here 9 teams have received 275K support in each in the 2 stages, and the 6 lucky ones will get in the end up to 500, almost 600K euro in the 3 stages. It's an added value of the challenge experiments because we're able to benchmark new algorithms on these first-class 3 hosting platforms. I forgot to say that the first one, the human-robot cooperation, is hosted by the group of Martin Hegele at IPA in Fraunhofer, the second one by Christian Ott at DLR, and the third one by Roland Sigwart at ETH in Zurich. So we had on board from the start the end users, the technology developers, and the system integrators. We have, of course, we assured open access to platforms, and it was a full scientific and technical support from the local host and the end user. And now, in the final stage, the test algorithms are being tested at the field. Financial support was mainly, the equipment was already available by the challengers, so mostly the money went to cover personal and travel lodge costs. The exercise of forming the challenge team was quite effective because also was an opportunity to gain business experience, and also, as usual, great network of opportunities. I don't have time to go into the 15 finalists, but just I have one slide for each challenge. So the first challenge, which is challenge aimed at production, those are the 5 competing teams, and Piros and Flea are the 2 finalists in the third stage. And you will hear something more from Piros that we invited to this presentation. In the second challenge, which in one word is about logistics, those are the 5 teams that competed in the second stage, and RSA2 and Team Iris are the 2 finalists. Actually, the work was recently completed last week, and so now it's the time to really report results and have a board of judges to select the symbolic Euro winner. In the third challenge, it's about services. Those are the 5 teams that compete in the second stage, and Tomb Flyers, the team from Technical University of Munich with the end user, and a group of Hannibal Olero in Sevilla at Catec. Those are the 2 finalists in the third stage for the plant and servicing challenge using aerial technology. So I leave the word to Federico, and you will hear just one step change as a sort of success story out of challenge 1.
Thank you for the introduction. Good morning, everyone. I am here representing Piro's team on behalf of all the people that during these years made a great effort to bring our solution into the field. We recently got the final deployment of our solution in the shop floor. So these are our partners, all the people involved. Just to give you a quick introduction of the use case, we are in challenge 1, the reconfigure manufacturing challenge, and we selected as the scenario the machine tool and machining sector, which is a primary economic sector. The impact and the size of the market is remarkable for Europe and worldwide, of course. The impact is expected to be high for introducing robotics in a relatively manual domain. A lot of automation is there, but collaborative robotics is relatively has a low rate of usage. And just to give you the quick overview, this is the system, the final system, where you see operators, a very skilled one, in charge of performing a lot of manual tasks that are kind of already. Yeah, a lot of manual tasks, heavy duty and complexity. So in a nutshell, the purpose was to introduce a collaborative platform able to support the operator, exchanging tasks. So instead of having a fixed task list, robot and human could share and to reschedule dynamically their purposes and their tasks. And fundamental to this objective was the involvement of the end user. This is a key message from the project and from our experience that I'd like to share with you. First of all, you see here in the video the deployment of the solution on the factory floor. This is one of the end user performing their regular operations. The commitment of the end user has been great, and Giuseppe Fogliazza is our end user, and I invite you to follow his longer presentation in the industrial robotic track later this morning in the late morning session, because we developed over the years a shared vision about collaborative robotics into the machining domain, so to share and to free the human, to really empower the human with their added value abilities. So this is a very step change in the machine tool sector. I invite you all to listen to his talk later. But one important thing beyond the vision that we share with our primary end user is the involvement of our second end user volunteering to join the team for making available their facilities to be involved in the deployment of the application. And we spent several weeks in their plant, merging our solution with the production line operational. I mean, a factory floor fully operational with the system in service. It was not easy because if many of you have experience in integrating with the end users, you know that the real engagement, the time spent is not a common thing. In this case, we got full support, several days, several weeks of full support and cooperation in a noisy, productive environment. So it was a great experience to share with them a daily life of development, debugging, fixing, working, really hard work. Why they got us so much support? Because they really wanted to understand the boundaries of these applications for their purpose, and both of the end users. And I must say, concluding, that they are still working. After the demonstration and the field test, the end user got the solution back. They are preparing for being part of their portfolio for promoting this kind of solutions in their vision to the market. We will have several trade shows and dissemination of the platform to have in mind to keep it operational over the time. What we got, a very quick remark about the project, the pressure of the challenge was remarkably important for getting results, especially the metrics, quantitative objectives were very functional to get us on purpose and stay focused to get really deployable and relevant results. So the face value of the application is what is really behind all the consoles and things running. Thank you for your attention. It was great.
And so the final...
Last but not least, yes.
Yeah, the next steps is there will be the final challenge workshop, which will take place in Naples from April 5th to 7th, in which the results from the 6 finalists will be judged by an independent board of judges, international one, and selection of the Europe winner. And the results will be showcased at the Automatica Fair in Munich, in which the actual award will be given. And there will also be a nice video produced reporting the results of the project. So see you in Munich in June. Thank you.
Thank you so much. Thank you very much. Month of time very limited. I suggest we move to the next presenter. In any case, there will be after this a poster session, so people were invited to bring a poster, so you can meet them afterwards. So, Nicola?
Hello, good morning. Thanks, Cecile, for this opportunity. I will contribute to to save part of the time. I'm here representing the CyberLex++ project that actually has academic partners, Scuola Sant'Anna, Université Catholique de Leuven, and Vrije Universiteit Brussels and University of Ljubljana, and a rehabilitation center, Fondazione Dognocchi, and 2 companies, one large company, Ossur, and a small medium enterprise, Juvo. The ambition of the CyberLex project is to actually improve the quality of life of people living with amputations. You know that amputation of lower limb in particular is really devastating for the life. It's very fatiguous to walk around, to go up and down stairs. And the idea of the project is to, the vision is to develop new prostheses and new orthoses, helping amputees to have a more efficient movement ability in a real-life application, in a real-life scenario. We started, and we start from the results of a previous FP7 project, the CyberLex project, that actually had 3 different levels of results. We developed the new technologies for series elastic actuators, so we really worked out new actuation principles for both orthosis and prosthesis. We developed new mechanisms and transmission means for orthosis, and a huge effort was also devoted to develop new wearable sensors and control strategies for understanding what the human and what the user wants to do. Basically, on top of that, we integrated and developed the prototypes of prosthesis and of exoskeletons. Mostly the 2 more relevant technologies were transfemoral powered prosthesis and what we call an active pelvis orthosis. Based on this technology, we actually collected several proof of concepts of our vision In particular, we could validate that this kind of technology can be used also to mitigate the risk of fall. There was a nice paper published on Scientific Reports a couple of years ago. We validated that motor primitives can be used to smoothly and gently control prostheses and exoskeletons, and also that these technologies can be used to actually improve the gait efficiency of amputees. Actually, in the new project in CyberLex++ that started actually 1 year ago, the idea was to move from TRL5, so from this proof of concept, to something that is much more close to the real use actually closer to the market, by means of a strategic collaboration between academia, industry, and clinics. So that is what the innovation action in Horizon 2020 are actually expected to achieve. So the specific objectives of the project, I don't want to bore you, but actually there are 4 objectives. One is to further develop the hardware and software modules that were developed in the previous project. So this means improving robots. So we all are roboticists, and we all know how much time it takes to work on the hardware, work on the software, and get continuous improvements. In particular, on the software to get it really reliable, and then to carry out clinical studies, so really experimenting the technologies with the end user. And last but not least, since the support that we receive from the European Commission is ultimately useful if we can create new business opportunities and new market opportunities to foster actually a reliable exploitation strategy. So this is the structure of work packages. Actually, I like to say that we just ended the first year and we positively, it was quite a success, the first review meeting that was held in Florence just 1 month ago. And you see, basically, there is a lot of work packages about development. So unfortunately, I cannot show you many details and I cannot show you a lot of results because the project is really at the early stage. However, there were 2 results achieved by the project in the first year. One is about communication. So last year we were in Tallinn during the Digital Summit, and we were one of the few projects that had the opportunity to show the vision and the challenge and the results to several leaders in Europe. I had also personally the honor to talk to the Prime Minister of Italy and Greece. And actually another important achievement is that one of the partners of the project, Juvo, actually received a very important investment from 2 large companies, Ossur, that is also a partner in the CyberLex++ project, and Comau, that is a leading Italian company in the field of industrial and robotics automation. In robotics and industrial automation. And the idea of this investment is that we really want to bring exoskeletons in the real life. Actually, Juvo has the ambition to become a leading company worldwide and really compete with companies like Samsung, Honda, and other big players in Asia, like Toyota and Panasonic. So this is a real challenge, and this means that we have to be really committed to take not only the scientific part of the story, but also the innovation part of the story very seriously into account. I now leave the floor to Dr. Torstensson from Ossur for the concluding part of the talk.
Thank you, Nicola. The approach to innovation in the CyberLex++ project was in the way that we tried to be a little bit formal. We appointed an innovation management panel with 1 representative from each partner. We called for the innovation policies or innovation management policies from the partners. Of course, they're a little bit different between companies and academia, but we think that we have managed to sort of compile that into a policy that aims at preserving or protecting the IP when it arises, but still publishing as widely as we possibly can. And we try to foster the open discussion about the potential innovative concepts that we have. On the marketing side, we have tried to start to map out what is the market, what are we aiming for in the short term. That's of course, as you may have guessed from the presentation so far, that we will look into the prosthetic market and certain parts of orthotic markets to start with. Longer term, we want to widen that out in the rehab and personal use market in O&P. And the longer term, what we call indirect market, is then the use of components from the systems that we have in other fields. Just to mention on the protection of IP that we have, in the first year, we have had 7 concepts that have been discussed for potential protection. That has resulted in 1 filed patent application and 2 patent applications that are being prepared. And we still have 4 concepts that are under evaluation and most likely will be applied for patents on. And that concludes our presentation.
Thanks a lot. Thank you. Very interesting. Thank you. And it's good to see that you managed to have dissemination, scientific dissemination, together with exploitation. So that's thank you. Thank you. So I suggest we go to the next one quickly. The next one is you, Sami. So it's about a success story. A few years after the end of the Safari project, what was the result in this company, Sami's company, and so tell us your success story.
Yeah, thanks, Cecile, for the nice introduction. First of all, thanks for having me here. I'm in a bit different role. Can I take this away? Just to put it there. Great, thanks. So I try to bridge a gap here between a very nice and very, I think personally, very successful European project. Thank you. So let's see. Yeah. So Safari, which was really an honor to work with many of the colleagues that you all know. And I'm trying to give you a very bird's eye view on where things were going, what was the overall objective, and where does it come from, and where did we arrive just recently. And yeah, it ended kind of into the biggest honor you can actually get as a scientist, I guess, in Germany. It ended into the German President's Award, which we recently received. And I think this was also a very nice result out of the Safari project a couple of years after, but also for robotics in general, showing that it could reach this kind of attention and this kind of maturity. So when we started Safari, and maybe even a couple of years before, then obviously we all were kind of in this industrial phase of humans, robots being segregated. We had these huge industrial robots, which are still majorly being used. However, other things are increasing at the moment. But most robots back then, they were sold, I mean, essentially 95% or 98% were industrial robots behind fences, position control, doing pick-and-place tasks maybe, but mostly spot welding and painting. So all these systems could not do the major things which we all would like to do, meaning assembly, for which we need a sense of touch, obviously, as we all know in this community. And this was also, and is still to a large extent, the reason why we basically lost our entire electronics manufacturing to the Far East, because all the processes for which we need our sense of touch, our compliance, our learning of motor skills, was kind of not being able to be automated, at least in real life. So essentially, if you want to do some screwing or assembly tasks, you had to outsource it, and therefore most of the processes that require especially 3C manufacturing tasks, which is by the way the largest market in the world, 10 times bigger than automobile manufacturing, essentially went to Far East. And obviously this is also a major reason why the small and medium enterprises in Europe kind of have a very big disadvantages regarding labor cost, because these things have to be done manual, and only very very high qualitative work can still remain here in Europe and in Germany. So this is kind of the main reason why many of the things we created were developed on a very high level and economical level. And I think the major thing is if we can kind of automate the things I'm showing here, then we kind of contributed a lot towards bringing back manufacturing to Europe, to Germany, but also to kind of solve a very big ethical issue that I personally see, and I think we as roboticists should really take this very serious. It's kind of the way that we treat the manufacturing by outsourcing it essentially creates obviously very big ethical problem by having companies that have hundreds of thousands of people, maybe even more than 1 million, that essentially do jobs that we would personally, I would call this modern labor, slave work. So this is obviously something that correlates. So the disability of us as a robotics community to create robots that can do assembly tasks and the numbers of people because of the growing demands and the growing markets that have to basically do works as we see here under very disturbing circumstances. And I think another potential opportunity I see for robotics at the moment is that we actually can go back to the way that we should see the potential behind robots and kind of be able to work on creating a better life in some sense, right? We talk a lot about quality of life, and I think we have to talk about quality of life not only locally in Europe and in Germany, but also worldwide. And mankind was always very good in creating tools that basically make our lives easier and simpler and better in the future. And I think if we take it to a very high abstraction, then I guess one of the biggest challenges and I think at the same time potentials I see is that robotics can kind of contribute to freeing mankind of slavery, maybe not in our circumstances, but in the other worlds where we basically outsourced our very kind of low quality labor that is, as I said, taking place under very questionable circumstances. And in order to do this, we obviously need, and now I'm coming to the Safari project, we need to be able to physically interact with the world, we need to be able to safely interact with the world, we need to be able to basically use the sense of touch in a purposeful way. And this was the main kind of objective of the Safari project. Safari stood for Safe and Autonomous Physical Human Aware Robot Interaction. And it was led by Alessandro De Luca from University of Rome, one of our highest esteemed colleagues, obviously. And he did a wonderful job in putting together a team. And many of you are here, of course. I mean, just to name Bruno, Antonio, Nikos, Rashid, and so on and so forth. Michael Beetz at Bremen and TUM, Aline obviously at DLR, and I was myself also back then at DLR. And this was a wonderful group of researchers, also together with KUKA. We kind of had a great, back then, German manufacturer on board. And the major goal was essentially to put the human at the center of the design of a robot. So what we called human-centered robotics. We essentially even formed a group at DLR back then to do this. And the main idea was to really do all the design steps of a robot, ranging from compliant mechatronic design towards perception, interaction control, learning and interpretation, reactive action generation, human-aware task planning, and safety around the human itself, right? So really creating assistance to the human user, and this was the major goal we had. And there were several larger results which came out of this project, among which the basics of safety were around, so which kind of forming the basis for the ISO 10218 or TS 15066 standards and technical specifications. Kind of we led the basic scientific work there, and it led actually to something which we called the Handbook of Injury in Robotics, which was one of the final deliverables of the project at month 48 back then. But I also want to point out that Safari was also a step in a road that we took together. So many of the people in the project were working together for many years. So we had two projects that were proceeding, essentially Friends and Viactors, which also contributed to a large extent to the success of the Safari project. So we could build on friendship, on very good technical and scientific expertise, and we're really a very, very good team in Safari. And I think this was also a major reason why we were succeeding. And I just want to show you some things that we did back then at DLR, kind of within the Safari project, and obviously also in the Friends project and before, but also the basic research. I mean, Safari was a very huge project, but I just wanted to show you some impressions what kind of led then to the technology development of Franca Amica. So all the things for collision handling, collision detection with Alessandro, we looked at kind of these collision tests that maybe most of you know, how to basically make robots safe, how can we relate mechanical control parameters towards human safety, how can we actually make robots such safe that we understand what is it that potentially hurts humans, and how can we prevent the human from hurting prevent the robot from hurting the human in an entire task. Interaction control was to a large extent developed there also, which we see nowadays more and more, the fusion of of AI and robotics, we were actually very early with these things, so connecting planning and programming levels with controls, developing novel co-working concepts, talking with the robots via physical interaction, via multimodal interaction, robots doing gestures for very intuitive communication to basically present the internal state of the robots towards the human, and being able to connect physical interaction and control with the planning and the programming level, which was, I think, another thing that we did together with Michael, for example, Michael Beetz now at Uni Bremen, and also with Dongyi from TUM back then, and many others were involved on the perception level. So we basically pioneered the work of collaborative human-robot assembly. So we see nowadays more and more AI technology being connected with robotics, but we also did it back then, already very early stage. So human-robot interaction patterns as a basic pattern or control pattern that basically facilitates planning of interaction schemes that makes it possible to detect and react to unforeseen incidents, not only on control but also on planning level, so in order to basically have co-workers that don't have to stop the entire line if you have certain disturbances, but the robots and humans basically plan and autonomously do tasks together. And having developed all these technologies kind of led to the idea when I was back then at Willow Garage, so I want to point out also to Steve Cousins, who was kind of a very great supporter of the idea of spinning off back then from DLR, and Hirzinger, so back then still the boss of the institute, and Aline were very supportive. There was just the transition phase when we kind of decided, let's take this to the market and let's try to really bring something to reality that makes it possible to kind of create a great technology out of the Safari project results and other things we have been developing so far. So we spinned off a company called Kastanienbaum, which was the basic incubator. I back then moved to Leibniz University in Hanover, and we essentially kind of contributed a lot and further developed the technology we have been creating so far, and it ended up in the so-called Franca Amica company that basically creates the robot Panda that I'm going to talk about now for the last couple of minutes. And just recently, so in a couple of weeks, I'm going to move now to TUM to be the director of the Munich School of Robotics and Machine Intelligence, so kind of contributing further on research so that we actually drive these technologies further and take it to the next level. So the major goal that we had was to basically be an enabler for the next big economy. So how can we take this basic technology from the Safari project further and design affordable commodity automation for SMEs and private sectors, and make this an enabler to basically bring back production to Germany. So the result was the Panda system, which is now being commercialized by Franca Amica and produced. So the idea was basically to have a robot assistant that is interactive, safe, that is connected, has learning abilities and is sensitive, so obviously has a sense of touch, and can be used by basically ordinary people. The basic things, I guess, that are inside, you all know these basic works we've been doing, and these obviously are there as well. So human-like dexterity, safety reflexes for collision reflexes, virtual walls, and also the idea to basically do the sensitive insertion and manipulation, which you see on the lower right side. The major contribution was also not only on the mechatronic and controls level, but actually on the programming level. So we actually have designed new programming languages and programming interfaces that now can be used by basically normal people. You don't have to be an expert. We have now children programming robots that do assembly tasks that are more complex than what you see in industry nowadays. And this is kind of live programming of a pick-and-place task, just a couple of seconds. You basically use predefined apps that come within a kind of template. So this is essentially what could now be used by AI planning to create this automatically. And interestingly, this is a project that I support very much personally as well. This is the first time that the Panda system is being used in a company called Puki. They create bicycles for children, and they have a factory of disabled people. And he's actually, for the first time, having the robot in his hand, is able to create programs. So this actually shows how easy it is to use the system, and we have now even schools all over Germany being using these things. But the most important thing is that not only pick and place is now being able to be automated, but actually all kinds of assembly tasks. So you see all the electronics manufacturing, so the things you usually cannot automate, right? So this is now possible. You see on the lower right the iPhone testing, on the upper left the electronics manufacturing and assembly tests, which you see from all the big manufacturers you all know, and testing of electronics. So all things that needed to be created by human programmers, however no experts, basically normal people. Okay, and then another thing that we are particularly proud of, it's actually the first mass-produced robot that is not being created and manufactured in China. So it's actually, we opened up a new site. However, it was an old site, which was previously Nokia Siemens, so lost production facilities in Germany of electronics manufacturing. And we now brought back manufacturing robots and humans creating robots in Germany. And I think this is a great story to tell. Also, a part of the Safari results we have been doing actually created manufacturing and robot manufacturing jobs here. And we expect that by the end of the year, the robot will be the most sold robot in the world by means of one model. Final things I want to point out, because I'm now running out of time, is that the robot is also very affordable. So the basic version is below 10,000 euros. So we actually wanted to bring highest technology at most affordable prices, so to democratize essentially automation. And it has very low setup and integration costs, and you can basically have hundreds of robots deployed very easily just via a cloud system that you see on the right side. That's browser-based, and it really gives you global access to the robot apps that I couldn't talk so much about. At Hannover Fair in a couple of weeks, you're going to see the first CE-marked systems that really come as a solution. That's a novelty in robotics, and I think I want to point this out. And the last thing I want to point out is that you see now that the orders of magnitude we could reduce the cost, and the way that I kind of skipped this entirely, but I think was also very important is training young children and training also the workers of our manufacturing sites to create these systems. And this was actually a young girl for the first time seeing a robot and being able to interact with it immediately. So we basically need to create something that I call the robotic natives. So young children that grow up with robotics technology to create basically the future of our continent and our countries. Thanks a lot. And this is the final slide.
Impressive. Thanks a lot. Now we move to the last presentation about the long story of about ICAP, and back to this PC and that's it. Thank you.
So a long story that I'll present in 12 minutes because of coffee, especially.
Yes. But we can continue over coffee.
We can continue. I'd like to jump back actually in 2004 when the ICA project was started, or at least the first funded project was started, which was an FP6 in fact, and I have a little old logo from the cognitive system unit, was the name at that time. The project was called RoboCub. It was 11 partners. At least for us, was kind of an experience because it was the first large enough project. We had a company, and which is part of the story that I'm telling you today, called Telerobot. It's part of the story because it was the only company in the project and was helping partially with the mechanical design, but also in part with telling us how to do, for instance, documentation, so that the robot can be reproduced many times. It wasn't just one-off, as often, at least at that time, with the robots designed and in a single lab. Here the idea, there was also another, let's say, new idea, I think, at the time. There was an open call as part of the project to build copies of the robot to be distributed to winners of the open call in order to seed this idea that the robot could be reused in different places, sharing a common software platform. The project ran for 65 months. And so was long enough to allow the design of the ICAB, a hardware platform, both in mechanics and electronics, and software, and do some research and have enough time to run an open call and build a number of robots and distribute them to the winners of the open calls. I mean, you can recognize some of the people here that participated to the project. Nikos, for instance, Paolo and Cecilia that were also part of this project. And unfortunately, the person from Danieli Automation, Telerobot Labs, couldn't be here today because was supposed to tell the story of how, starting from the ICAP, we ended up now on several applications. Well, anyway, what we done on the RoboCub project was, of course, to design hardware, and but especially for this story, what was important was the design of sensors. And in particular, I think the iCub is one of the few platforms these days that have a full body sensorized skin, at least on the category of humanoid robots. There are not that many robots that can support a full coverage of the body. We have about 4,000 sensing points, which is a good enough number that can be used for instance, in Codico was used to develop these controllers, the estimate forces, also utilizing the skin. Another decision that I think it was quite nice in RoboCub was to be open source. This allowed us to create a small community of users that keep using and developing software for the iCub. As part of the project, though, we did quite a lot to build software good enough that can be reused by other people. This was part of the contribution from Telerobot Labs. This is actually the hand of the guy who designed, the daughter of the guy who designed the hand for the iCub. You can see the similar size. Actually, his daughter was 5 years old at that time, so he copied basically the hand in size. And as I say, more importantly, was the fact that we designed a skin for the iCub. This is an example how the body of the robot is covered with sensors. The technology is fairly simple. It's capacitive sensors, exactly like in the smartphones, nothing different, with a few modifications to make it flexible so that we can cover a robot that has a complicated shape, and also to be sensitive to objects that are not fingers, because we wanted the robot to be interacting, for instance, with plastic objects. This is a short video showing how the skin responds to touch, and actually you can see to the right that the response is pressure information, is analog. It's not just on-off. It's not just the contacts. So this information, as I showed earlier, can be combined with traditional force-torque sensors, and this leads to, for instance, compliance control or force control. This piece of work that was kind of in the air when we were running RoboCub, but was clearly perfection and made a lot better during Codico, as I was mentioning earlier. This piece of technology that is reusable, it turned out to be made into a set of libraries that are part of the iCub ecosystem, in a sense. The other piece of technology, since I mentioned open source, was the development of a middleware. Bear in mind that when we started, it was before ROS, so there was no ROS available. And so we developed our own middleware because there was no other way, actually, to integrate the work from many partners. 11 partners, 10 of them developing software. I mean, it was very, very difficult otherwise to integrate things. So we developed something called YARP. The name stands for yet another robot platform. At the moment, it's a very stable code base, about 400,000 lines of code, very well controlled. And as part of the development, we made also extensions, for instance, to real time, although at the moment is soft real time, and also unit tests. So now we can run not only the continuous integration type of thing that is typically done in many projects these days, but also we can develop tests for the software and run automatically with the iCub simulator. So we can basically guarantee that a certain level, which is not reality, it's still a simulation, we can check whether the software behaves. There are, at the moment, the repository is about 3 million lines of code overall, taking into account, for instance, the libraries that were developed as part of other projects. Our Codico is one example, library for inverse kinematics, for dynamics, whatever has been developed on the iCub. So it's fairly large. And this attracted the attention, in a sense, of these people from Telerobot Labs, Daniele Automation, and we started discussing. I went visiting their plants. We started discussing possible applications using what we developed for the humanoids in concrete scenarios. I don't know if you know that, but they build plants for metal production, and these plants are large objects, and they are very harsh environments. In particular, temperature is kind of problematic, even for the robots. I mean, there are places where easily have 500, 600 degrees, and not talking about the metal itself. It's just around the structure where they're melting the stuff. So it would be nice instead to put people away from this potentially dangerous environment in a nicely air-conditioned environment where they can have a console and can teleoperate the robots and can control what happens without having to be close to the actual metal foundry or whatever. So we discussed with them and we decided to go for a joint laboratory. And this is a fairly interesting way, at least for us, of doing a mix of research and move the research towards application. So the laboratory is funded for 2.5 million. It will run for 4 years and will basically take what we've done for YARP, the software of the ICAP, and force control and apply it to industrial robots. So it will be a way to take very large robots, apply force control on them, and run everything on YARP so that they don't have to depend, or they will have the flexibility of having a proper middleware to integrate different components. We'll be adding cameras, maybe lasers, different components. Robots also different brands because they have different brands in their plants and they like to recycle what they have and so forth. This is an example, a picture showing one of the applications. One thing that we'll be doing as a starting point will be, for instance, going there with a robot and putting a sensor into the melted metal, and taking measurements from that. And the problem is that the metal is not entirely uniform. You have to sense whether you have an obstacle while you put in the sensor in. And the risk is that if you stop there, you may melt also the sensor, so which is not good because then you have to stop the process and you don't get any measurements actually. So what we'll be doing as part of this joint laboratory will be, as I said, force control. Everything has to be fast. 100 microseconds is their control cycle. Not that we need to do force control at that speed, but the entire plant runs with that time granularity. So we also have to comply with this. For instance, message passing has to go with this 100 microseconds. And as I said, everything has to be flexible. The entire thing has to run on any possible robot or with a variety of robots. I'd like to finish with a bit of, let's say, a little take-home message, which is the following. Although research projects are, or at least I feel like that, often are like herding cats. I mean, you have this tension between researchers trying to go their own direction at random and the necessity of integrating in order to produce concrete results. I think it's still worthwhile. There are ideas that over the years consolidated, and given the opportunity, there's a chance to go to applications. This is happening, at least for us. It's not only with Daniele Robot Labs. I must say that recently we put in more effort on applied projects than entirely research projects. We've been very, maybe, successful with doing that. I think at the moment we have, I think, given the budget that IIT is putting on my lab, we're getting 70% more on industrial projects, which is, I think, a good percentage. And so, go for coffee. Thank you.
Thank you so much. Thanks a lot. So thank you, everybody. And then some of the project brought posters, so you can visit them in the coffee break. I want also to say that for the new generation of projects which were presented yesterday and will come in 3-4 years from now to present their success, so we have brochure for those projects there. So it's a little booklet with all the summary of the 23 projects we presented yesterday. And I want again to thank all the presenters for having shared the result. And I wish everybody to come later presenting their success as well when time comes. Thank you again and have a good break.